Okay, we're going to continue on here. So during lab, we wrapped up chapter 15, which was the last chapter again on our upcoming exam next week. That covers 14 and 15. So we're going to roll into here chapter 16, and we're on the downward hill here from all that buffers, titrations, and all that good stuff. So we'll get back into maybe a little bit more normal type stuff, like some formulas and plug and chug type of situations as we come through these final few chapters. So this would be our exam 3 material here that we're going to start. So we're going to go to chapter 16, which is about thermodynamics. And in thermodynamics, we get to use some more of the alphabet, which is nice, other than K. We will talk about entropy, which is delta S. We'll talk about Gibbs free energy, which is delta G. And of course, we can't go too far without tying them into our K value as well. In terms of thermodynamics, which is sort of what we will be talking about in this chapter, you already learned, hopefully, the first law of thermodynamics, which is our conservation, right, of energy, where energy is neither created nor destroyed, but can be transformed from one form to another. The major sort of component of that that you learned, obviously, is delta H, which is our enthalpy. Remember that our enthalpy and entropy, as we will talk about in this chapter, are different things, even though they kind of sound the same. Our delta H of our reaction can be calculated in a number of ways, but very commonly, we will take the delta H of our products, right, minus the delta H of our reactants. And depending on sort of the value of delta H, will tell us whether or not it is a exothermic reaction or an endothermic reaction. Really not necessarily the value, but the actual sign that we see for our delta H. If we get, again, a delta H that is negative, that is a exothermic process, which means heat and energy is being released. If we have a delta H that ends up being a positive value, that is an endothermic process there. We could get it by really doing products minus reactants. Could also calculate delta H, something like Hess's law. We could also calculate delta H using some type of thermochemical equation as well. A reminder that delta H, much like a lot of these other sort of thermodynamic values, are what are referred to again as state functions, right? And state functions basically mean it doesn't matter how you get there. The important things, again, is where you start and where you end. And that is when we talk about a chemical reaction, where we start our reactants, right, is basically our starting. And where we end is really our products, right? So that's why a lot of these thermodynamic sort of properties, the way that we calculate it, is to do products minus reactants. Basically, our final state minus our initial state gives us our change in enthalpy. Any questions on that there? Okay. So let's talk a little bit about spontaneous processes. And first off, let's talk about really the idea of spontaneous. And in thermodynamics, oftentimes what we are looking for is to sometimes answer a fairly simple question of, is this reaction spontaneous or non-spontaneous? Is sort of a lot of times what you're looking to sort of answer. It is important to remember that if a reaction is spontaneous, it does not necessarily mean that it will occur like super fast. It just means under those conditions, this reaction should take place. It may take place really fast. It may take place really slow. But basically, if a reaction is spontaneous, that's really what it means, which is it should take place. How fast or slow a reaction takes place is something that we talked about earlier on in the very first chapter, which is kinetics, right? Kinetics deals with the idea of how fast or how slow a reaction takes place. Reaction being spontaneous, again, means that it will just occur. There's lots of spontaneous reactions that are like super slow, and you can speed it up by adding something like a catalyst to it, but they are still spontaneous reactions that will occur. And there obviously are spontaneous reactions that are really, really fast as well. So there's a lot of physical and chemical processes that are spontaneous that we're aware of. Obviously, water runs downhill. We don't usually see water going up the hill. We know if we put sugar in a cup of coffee, it will dissolve. The standard sort of temperature and pressure for water to freeze and also melt is 0 degrees Celsius, which is a normal melting point and freezing point for something like water. In terms of energy and heat, as you probably learned, right, heat always flows from the hotter object to the colder object, right? The hotter guy gets colder, colder guy gets warm, and maybe if they are like in an insulated container, they meet somewhere in between. A gas expands in an evacuated bulb, and iron exposed to oxygen with a little bit of water will basically start to rust sort of spontaneously as well. Obviously, skiing, I suppose just going over the hill there will spontaneously send you down the hill, which is spontaneous. You can't really go up the hill like this guy in a spontaneous fashion. That's more of a non-spontaneous fashion. You need something to help you out, right? And I suppose if you're this guy, you don't want to see that guy coming up the hill as you're coming down the hill, as bad things might happen. Couple other sort of spontaneous versus non-spontaneous events. If we have a bunch of gas molecules in sort of a container, I think you could actually see the container on that, just good. And we have sort of a valve here, and if we kind of open the valve, you know, spontaneously, those gas molecules will basically sort of flood the other side of the container. Non-spontaneously, if we have sort of these guys, you know, on both sides of sort of the container, really, in most cases, they won't all decide to come this way without perhaps a little bit of coaxing over there. So in a non-spontaneous way, they pretty much won't go to the other side just by themselves. You can maybe force them to the other side, but probably not by themselves would they go to that other side. So when we look at spontaneous, or is a reaction spontaneous, what should we sort of look at to help us decide whether or not, you know, we will think that this reaction will be spontaneous or not? And can we look at enthalpy as sort of a measure of whether or not a reaction will be spontaneous? Once again, enthalpy being our delta H, either being negative, which would be exothermic, or positive, which would be endothermic. So if we look at a bunch of these reactions here, these are all spontaneous reactions. So we have basically the combustion reaction of methane, which is basically what happens when you light your Bunsen burner. We actually have the formation of water, and both of those processes here are exothermic, as they have negative delta H values. We also see some processes here where they're more of a endothermic sort of situation. So if we take some ice, it will start to melt spontaneously, right, into liquid water. If you take an ice cube out of the freezer and just leave it outside, it will pick up all the heat from the surroundings, right, and it will start to melt. And that's an endothermic process. That's the heat of fusion that we see there, 6.01 kilojoules per mole. The process of dissolving something like ammonium nitrate to make an ammonium nitrate solution also is a endothermic reaction. So what we see with these examples is you definitely can have a spontaneous reaction that is exothermic, but you could just as easily have a spontaneous reaction that is endothermic as well. So delta H is not necessarily the best thing to use to determine whether or not a reaction will be spontaneous, although exothermic reactions and processes does sort of favor spontaneity because obviously you're giving off energy, right? So that helps a lot of things sort of occur, but it doesn't necessarily guarantee it. So again, you could have a reaction that is both endothermic or exothermic and still be spontaneous regardless of the delta H values. So there is another sort of thermodynamic value that we should perhaps look at to maybe help us make that decision as to whether or not a reaction would be spontaneous. And another sort of factor that we can look at is what is known as the entropy. And the entropy is abbreviated with an S. And a lot of times it is the delta S, which is a lot of times, as we will see, our products minus our reactants is one way that you could calculate it. And what is the entropy? Entropy is really the measure of disorder or randomness that a system has. When we talk about thermodynamics, right, we also talk about an important sort of idea of, you know, a lot of times there is a system, right? And there is pretty much everything outside of that, the surroundings, basically. So if you were doing a reaction in a beaker, your system would be the beaker, and everything outside of that obviously would be the surroundings. And a lot of times what we look at when we think about sort of thermodynamic sort of properties like energy is that flow from either the system to the surroundings or the surroundings to the system. In general, when we talk about sort of things flowing in terms of thermodynamics, energy, whatever it may be, work, there's usually sort of a perfect flow, if you will, which means, for example, in the case of energy, if somebody releases a certain amount of energy, say somebody releases 50 kilojoules of energy, something else will gain that 50 joules of energy. It will just be opposite for each thing. For one thing, it would be exothermic as it releases the energy, which means obviously the sign would be negative. And for whatever is absorbing that energy, it would be a positive sort of value as it gains that amount of energy. So if the amount of order increases, the amount of entropy will actually decrease. So entropy is a little bit different than maybe you normally think about things like after you think about delta H. A lot of times we think about delta H as negative things happening and stuff like that. But with entropy is a little bit different. The more order you have, or if you want to think about it this way, the less disorder you have, the lower the entropy value will be. It'll be more of a negative value for delta S. The more disorder that you have, which would also mean the less order you have, so the greater the amount of disorder, the more positive the value of delta S actually becomes. So the greater amount of disorder will usually result in a delta S that's positive, and a less amount of disorder, more order will usually result in a delta S that is negative. Another important difference, as we will talk about in terms of S and H, is actually units. Delta H's, which is the enthalpy, is typically in kilojoules. And as we will see, delta S is typically in units of joules. Now, although it may not seem an important distinction, we will definitely see some equations where both of those values are used together, which means you do want to watch units so you're not off by a factor of 1,000. You got to do some type of conversion usually. And usually in terms of giving the answer, you should give the answer that way. You know, usually S will be in joules and H will be in kilojoules. So if the change in entropy, the final state has more energy or more disorder than the initial, will result in that positive sort of value for S, and again, a more negative value as we go the opposite way and we have more order. One of the easiest place to see sort of the change or visualize the change in entropy or disorder is as we change states. As we go from solid to liquid, there is a lot more disorder that's happening, right? As you go from solid, things are moving around. and they go from solid to liquid. Things are moving on a little bit more. They're able to pass each other, which is why liquids are more fluid. And as you go from liquid to gas, things are completely broken apart from one another, which means they're flying around crazily, right? Which means there's a lot of disorder that occurs as you go from liquid to gas. So the entropy value would increase, obviously, as we go this way. It would become more positive as we head to the right there. Again, if you go to the left, it would become more negative, the delta S. So if we had to predict what's happening here as we go from the solid, which is ice, to liquid water, that is increasing the disorder, right? In liquid, again, things are moving more than they are in the solid state, and we would expect a delta S value to be more on the positive side in this particular case. Any questions on that there? So disorder is related to probability, and when we talk about probability, a probable event is one where there is many ways that something could happen. An improbable event is one where there's just maybe only one way for something to happen. So for example, if we were in this room and there was multiple doors to leave this room, it's pretty probable that we could get out a door and probably leave this room. If this room had no doors, it's a very small window, like in the top left corner of the room, and we needed to exit the room, that might be a more improbable event that we're going to get out of this room, as there's only one way kind of in and out through a very small window. So when we have a ordered state, in order to do something that's very ordered and you have a lot of long range order, there's a low probability of that occurring and a small entropy. There's really kind of only one way to do it right, if you will, to put it together correctly. And a disordered state has a high probability of occurring and a larger entropy. There's more ways to screw up, right, and do things wrong, if you will, right? So there's a greater chance that that will occur and it will have a greater entropy sort of value. There's actually an equation that relates to this, and this is sometimes referred to as the Boltzmann equation, and that is the equation in the box there. S is equal to K times the natural log of W. S is our entropy. K is our Boltzmann constant, which is there on the bottom. And W is microstates. And microstates are basically the number of ways that you could kind of do something. So the number of different ways that something can be, that can occur. And if we look at sort of the example that they show there in the picture, we basically have 4 circles. And if we wanted to put all 4 circles on one side of a box, there's really only one way to do that. Either you put it on the left-hand side or the right-hand side. It's basically only one way, which is the same. Basically, put them all into one box. If you wanted to do 1 circle in one box and 3 circles in another box, there's 4 different ways that you can accomplish that. And if you wanted to do kind of 2 circles into each box, there is 6 different ways that you could sort of accomplish that. So the one that would have the higher entropy is this guy. Yeah, this guy would have the much higher entropy because there's many different ways you could do that, right? So a lot of disorder that could occur from that. There's only one way to do this correctly, right? Which means small entropy, lower chance of that occurring. We could see that by just simply taking this equation and putting in our value here. So if we took this natural log of 1, what is natural log of 1? It is 0, yeah, which means we have a low entropy value basically of 0, which could just put 6 in there if you like. S is equal to K natural log of 6. Natural log of 6 is like 1.79, yes, which obviously will give us a much larger sort of value of entropy. So more ways of accomplishing something, the higher the entropy value. Less ways of doing something, the lower the entropy value in this particular case. So if our final microstates are greater than our initial, then we will see that a positive value for our change in entropy, and it's obviously the opposite. If we end up with less ways of doing something, we will end up with a more negative entropy value. Any questions on that there? So these are all processes here that are pictured that will lead to an increase in entropy, a more positive entropy value. Clearly, as we go from solid to liquid, we're fairly ordered. Again, having a little bit more disorder as we go into that liquid state, and then continuing the disorder as we go from liquid, obviously, to gas molecules, as these guys are basically just flying around. The process of actually making a solution is a process that increases the entropy for really both parts of the solution. Remember that a solution is made up of a solute, which is the stuff dissolved, and a solvent, right, which is the larger part of the solution. So before you dissolve anything, something that's ionic will pretty much be together in a nice, organized, long-range, ordered fashion of ions stuck together, right? Positive, negative guys, and these very repeatable patterns. Perhaps you remember talking about something like unit cells, maybe, yes? And in Chem 50, where you talked about sort of the repeatable pattern that you could actually just take a little portion of the solid and be able to rebuild the entire solid just from that repeatable pattern that occurs. Something like the solvent as well, say if that was water, before you dissolve something in it, you have a bunch of water molecules that are attached to other water molecules in a very organized sort of fashion through hydrogen bonding. In order to get everybody to dissolve together, you got to rip apart the ions from each other in the solid state, right? Which makes more disorder. You also have to break apart bonds between water molecules and water molecules. They got to go find some ions to help it dissolve. So it creates a lot more disorder both in the solute and the solvent when that occurs. As we change the temperature as well, and we increase the temperature, we also will see an increase in the entropy, because an increase in temperature usually is a result of an increase in energy, right? So as we increase the temperature, we're supplying a lot more energy, and when things have a lot more energy, they tend to start moving around a lot more, right, and creating a lot more disorder that will happen. And that's what we typically see at a hotter temperature. Things will have a lot more energy, movement, and disorder than you would at a lower temperature. All right, so take a moment for each of these and decide, how does the entropy change for each of the following processes? Does the delta S become more positive, negative? Is it increasing, decreasing? So take a moment and see what you come up with. So let's take a look. Here we're going to do condensating water vapor. So condensation is obviously when we go from gas back to liquid. So that is definitely going from a state of more disorder, everybody flying around, to a state of where they drop into sort of solution. They're not moving and flying around as fast. So that should definitely decrease the disorder or increase the order, whichever way you want to look at it. That also means that we should be creating more order, which means our delta S here should end up being more negative in this particular case. Any questions on that there? So our entropy is decreasing, right? The forming of a sucrose crystal from a supersaturated solution. So the formation of a crystal, the only way to make a crystal is kind of one way. We're basically making a solid in this case from a solution. That also is going to decrease the disorder. Also will result in our delta S being negative and our entropy decreasing, right? Heating hydrogen gas from 60 to 80 degrees. We're increasing the temperature. So as you know from your gas laws conversations, when you increase the temperature, the velocity, the root velocity of a gas will increase as well, right? It should start flying around a lot faster. That would increase the disorder, right? We got all these things flying around a lot faster. And that means that our entropy should be increasing and become more positive in that particular case. And lastly, here's sublimation there of dry ice. Sublimation is the journey from solid to gas, skipping the liquid phase. That obviously is going from solid, which is a pretty organized fashion, to gas, which is obviously a lot more disorder has occurred. So we're increasing the disorder. That should result in a positive delta S as a result of our entropy increasing. Any questions on any of those there? Okay. So let's talk a little bit about calculating entropy. As I mentioned earlier, entropy is a state function. And again, state functions only important things is really where you start and where you end. So potential energy, for example, is another example. Both of these hikers again started here. They both ended up here. The guy in blue took the more direct route up the hill. The guy in red took the scenic route around the mountain. But in terms of the potential energy, they basically have the same, as they started in the same spot, ended in the same spot. So their final minus initial is basically the same. Things like enthalpy, pressure, volume, and entropy are also those type of things. And as I stated earlier, basically in a reaction, our reactants is our starting and our product is our ending. So again, one way that you can calculate the entropy, as we will talk about here in a second, is to take your products minus your reactants. One thing that you could do is to basically look up these values in a thermodynamic table. There is usually a thermodynamic table, and there should be one in your book as well towards the end. And there usually will have delta H values, delta S values, and delta G values in there. And you would want to look them up in that table. A couple of important things about that table, or any thermodynamic table, which is you want to make sure that when you look it up, you find obviously the right substance, but you also want to make sure that it is in the correct phase that you are looking for. Things for delta H that are in their standard state and not combined have delta H values of 0. So things like O2, N2, and those type of things. The delta H values will be 0, but for the delta S value for those type of things, you will actually find a value. So there are values for delta S's for things like O2, N2, and things that are not combined. Another difference is entropy values are typically positive values, and they are also, as we were talking about earlier, they are typically in joules, which again is different than delta H, which is in kilojoules in terms of those two things. So we could look up entropy values in tables, and we could calculate the entropy to help us figure out whether or not a reaction is going to be spontaneous. So the first law of thermodynamics, which is what you covered when you did delta H, is energy can be converted from one form to another, but again, cannot be created nor destroyed. That again is that idea of sort of a perfect exchange of energy from one thing to the next. So whatever somebody loses, somebody else gains. The second law of thermodynamics is the entropy of the universe increases in a spontaneous process, excuse me, but remains unchanged in an equilibrium process. So in order to use entropy to help us determine whether or not a reaction is spontaneous, we do have to calculate something that is referred to as the entropy of the universe. And the universe is basically made up of two things. It is made up of the system, or sometimes the reaction is referred to, and the surroundings. So if you calculate the delta S of the system and you calculate the delta S of the surroundings, which we will talk about how to do both of those in just a second, and you add them together to get the delta S of the universe, and it is a positive value, then that will tell you that the reaction as it is written should be a spontaneous process, and that reaction should proceed probably as written to the product side. If you calculate the delta S of the universe and it is less than 0, or a negative number, what that will also tell you is obviously the opposite, that the reaction as it is written is non-spontaneous the way it's written and will not really occur going to the products. It basically will just stay there at the reactant side. If you calculate the delta S of the universe, and it equals 0, you are at a spontaneous, you're not at a spontaneous, you're at an equilibrium process. And in an equilibrium process, the entropy remains unchanged, because in an equilibrium process, what is happening? As fast as it goes one way, right, is coming back the other way just as fast, which means there is no net change that's occurring to anybody, right? Whatever it is at that point is what it is. And there's no net change that's happening in terms of something being released to the universe. So when we hit an equilibrium process, because the rate of the reverse reaction and the forward reaction equal each other, again, it locks everybody into place. As we talked about, there really is no change sort of occurring in that situation. Any questions on that there? All right, so let's first talk about how we go about calculating the delta S of the system. Again, it is also sometimes referred to as the delta S of the surroundings, not surroundings, delta S of the reaction. And we could calculate the standard entropy change of a reaction. By the way, that's what the little knot represents. Basically, you can think of it this way: the delta S knot, or delta H knot on top, the little circle on top of any of those sort of thermodynamic values, are really, one way you can think of it is, this is what is under sort of standard conditions. And they're kind of like table type conditions. And what we mean by that is, typically under standard conditions, if we're dealing with any type of pressure, that means that the pressures would be 1 atmosphere. If we're dealing with any type of concentration, the concentrations would be 1 molar. And typically, if we're dealing with temperature, the temperature is 25 degrees Celsius. So those are really sort of your standard conditions. Those are basically, if you look at most tables and in books and so forth that you look up values for, those are sort of the conditions at which those values were achieved under these sort of standard conditions. And that's basically the way you can think of this. When you see anything with a knot on it, is like, that's what it is under sort of standard sort of conditions. So basically, we could take the delta S of our reaction by taking the delta S of our products minus the delta S of our reactants. Again, final state minus initial state. We do, much like what you do with delta H, you do have to multiply the value that you find in the table by the coefficient in the balanced equation. So typically speaking, those values that you find in the table are like joules per Kelvin per mole. So if there is a coefficient there, say that guy's a 2 for the coefficient, you would need to take 2 times that, and that basically takes care of the moles part of it when you multiply it. So you do have to add up all the products, minus it from all the reactants, take the coefficients into account. And again, if you get a delta S value that's positive or negative, it will allow you to understand whether or not the amount of disorders increasing or decreasing in this reaction. So why don't you try one here? I feel like there's a value missing. It should be on your notes, right? You have it, I hope. There it is. I think on mine, I'm missing the CO2 here, right? So the S of the CO2, 213.6 joules per Kelvin per mole. All right, so take a moment and calculate the delta S for this particular reaction. Take a look at this. So again, pretty much in a situation for any type of thermodynamic problem, be it delta H, delta S, or delta G, as we will see shortly. And pretty much all you're given is the equation, and they're asked to calculate any of those things, H, S, or G. Pretty much that means go to the table and look up the values and do your products minus reactants. So that's what we would do here. Obviously, it probably won't be provided for you in a lot of problems. You will have to refer to a table to find these values. But we're going to take basically our products minus our reactants. So our delta S here of our reaction, our system. On our product side, we have 2 CO2s. So we'll take 2 times the value of CO2 here, which is 213.6 joules per Kelvin per mole. Then we will subtract it from our reactant side, which is CO. So we have 2 times the value of CO, which is 197.9. We then will add it to our other reactant, which is O2. Coefficient is 1. So basically it's 1 times 205. And if we do all that good stuff there, it looks like 2 times 213.6 minus 2 times 197.9 plus a 205. Going to give us a minus 173.6 joules in this particular case. If you want to leave the Kelvin there, you can. Joules per Kelvin, technically. The moles cancel out. In this particular case, this tells us, does this tell us if the reaction is spontaneous or not? This does not tell us if the reaction is spontaneous or not. This simply tells us in this reaction, is the entropy increasing or decreasing? So what is happening in this reaction? Is the amount of disorder increasing or decreasing? The amount of disorder is decreasing, right? So we're getting a lot more order. One of the things that you could do in a calculation like this is actually make that prediction looking solely at the equation itself. In this particular equation, we are starting with a grand total of 3 gas molecules, right? So we got 3 gas molecules flying around. We are ending with only 2 gas molecules flying around. So we went from 3 things flying around crazily to only 2 things flying around crazily, which means the amount of order is increasing, the amount of disorder is decreasing. And that is why we would expect this. Won't tell us the value, but we should expect it to end up as being a negative value for delta S because of that increase in the amount of order, and again, a decrease in the amount of disorder. So sometimes just looking at the equation, you can make a pretty good prediction as to whether or not, again, that order should be increasing or decreasing. But basically, that is what that value tells us here. Nothing about spontaneity. It's just telling us that in this reaction, we are seeing an increase in the amount of order that is happening. Any questions on that there? All right. So as I just mentioned there, you can make a pretty good prediction. And out of all the chapters that we deal with, usually the thermodynamics chapter is the chapter where they will ask you questions like that and not really give you values. They'll just say, hey, this thing is positive, this thing is negative. Would you expect this reaction to be spontaneous or non-spontaneous? Do you expect the amount of order to increase or decrease? So sometimes they'll just kind of give you those questions without really numbers and try to ask you what you think is going on. So sometimes it's easier to look at the reaction. You can make some pretty reasonable assumptions based on what's happening. So as we've been talking about, if a reaction produces more gas than it started with, so in that case, you would have a lot more gas molecules flying around than you did to begin with. That would increase the disorder, and we would see the increase in the entropy becoming more positive. If the total number of gas molecules diminishes, which is what we just saw in this previous example, we ended up with less gas molecules, so a lot more order happening. We will end up with a negative for delta S. If there is kind of no net change in the gas molecules, which could be the case, it may be positive or may be negative delta S, but it will be probably more on the small number. So just simply looking at the reaction on the bottom, would we expect the delta S value to be positive or negative in this case? So let's see, left-hand side here, we have a grand total of only 1 gas molecule, right? This guy. And over here, we have none, right? So we went from 1 gas molecule flying around to no gas molecules flying around. So that's definitely something moving to nobody moving in front of your eyes. Much more order sort of happening in that situation. And in that case, we would be increasing the order. And we would expect our delta S to be more negative, or obviously less than 0 in this particular case. Any questions on that there? So now that we talked about how you calculate the delta S for the reaction or the system, let's talk about how you can calculate the delta S for the surroundings. So the surroundings are a little bit different in terms of what is happening. And a lot of times the change in the entropy of the surroundings is related to what type of reaction you're dealing with, whether it be an exothermic reaction or an endothermic reaction. So over here on the left-hand side, we have an exothermic reaction, which is going to send heat and energy out to our surroundings. Now, when the surroundings pick up the extra heat and energy, will everybody in the surroundings be moving slower or faster? They should be moving faster, right? Which if you just visually think about it, if somebody's moving faster, that's a lot more chaos, right? And disorder. And that should result in our surroundings increasing the amount of disorder and having a more positive value for the delta S. Opposite is true if we see an endothermic process. That means that the system is actually going to suck out from the surroundings all that energy, and that means that the surroundings is going to lose that energy. So if you want to visualize the surroundings as like gas molecules, the gas molecules lose energy. They should be then flying around a lot slower, right? Which means they're going to be a little bit more ordered. And we would see the delta S of the surroundings become more negative in that particular case as we're increasing the order. So the delta S of the surroundings is proportional, that's what that symbol is supposed to be, to negative delta H of the system or the reaction. So let's talk about what that really means. So if we have a delta H, we have a delta S. If the delta S will be negative of the delta H. So what that means is if we have a exothermic reaction, there we go. Our delta H value should be negative, yes, which means a negative and a negative will turn our delta S into a positive for the surroundings. If our reaction is endothermic, our delta H should be positive, which means a negative and a positive will turn our delta S of the surroundings into a negative number. So it is basically opposite of our value for exothermic and endothermic in terms of the sign. Question on that there. So the question I have is the temperature of the surroundings to start with important in terms of the entropy change that you see? So let's say, for example, we have this situation here, an exothermic reaction, but my temperature, my surroundings is like really high, like a really, really high temperature. Will there be a really big entropy change from the reaction being exothermic in that situation? There will not, right? Because the temperature surroundings were really hot to begin with. Kind of like if you lit a match in, say, a regular room like this, and you put your hand near the match, right? You would feel the heat, right? If you lit a match, and don't do this, but if you lit a match and you put it into an oven that's on a very high temperature, right? The heat coming off the match versus the temperature in the oven, not going to probably see that much of a difference. Don't stick your head or body parts into ovens with lit matches or any of those things for safety reasons. But obviously you would not see a big change in obviously the energy coming off of the match versus the surrounding temperature to begin with. So the temperature of the surroundings does play a role. If it's sort of a normal sort of temperature and it's an exothermic process, you will see that change in entropy pretty much occurring. And if it's a normal temperature and sort of a decrease in that energy of the surroundings, you will see it. But again, the temperature of surroundings does play a role. Any questions on that there? So as I mentioned a second ago, that temperature of surroundings does play a role. So to calculate the surroundings entropy, let me rewrite it as it got messed. I think it's okay on your notes, but on my page here, it got a little messed up. So the delta S of the surroundings is negative delta H of the reaction, our system, divided by our temperature in Kelvin. Obviously, it needs to be in Kelvin. Now, you are still going to have some perhaps issues when you're doing this. Remember that delta H will probably be in kilojoules. You may want to convert it to joules so that your surroundings will end up in joules, but just keep in mind of units as you go through this, that you don't end up in the wrong sort of unit when you go to add things together. So also important is this equation here. In this equation, it is the delta S of the surroundings equals negative delta H of the reaction divided by the temperature. And that negative is there for a reason. It is there for that reason we just spoke about, the sort of opposite relationship that you see. The reason I pointed out is later on in this chapter, we will see this exact same equation, but there will be no negative. Yes, and people always want to put the negative there where it shouldn't go. So you should only have the negative here if you're doing the delta S of the surroundings. If you use an equation and solve for this, which is what we'll do later on, you don't put the negative in there. So again, very common mistake. Sometimes people will enter that negative in all situations. So we'll see something that looks very, very similar to this a little bit later on. So clearly, if you calculate the delta S of the surroundings using this equation, you calculate the delta S of the reaction using the other equation, that will allow you to calculate your delta S of your universe, right? Which again would be your delta S of your reaction or system, which is products minus reactants, minus the delta S of your surroundings, which is this guy down here. And again, that is the one that you could add together to determine whether or not the reaction is going to be spontaneous. So why don't we try one here? Take a few moments, calculate all of that, delta S of the system, delta S of the surroundings, and determine, is this reaction spontaneous? Look, and we want to calculate obviously two things: our system, our reaction, and our surroundings. For our system, we'll do products minus reactants. Again, if they were not given to you, you would have to go obviously to the table to do that. So let's start there. Our delta S here of our reaction will be, again, basically our products minus our reactants. We want to make sure that we do take care of the coefficients as well. So starting on our product side, we have two of the NH3s, which look like it is a 193. Then on our reactant side, we have just an N2, which looks like it is a 192. Plus our 3 H2s, which again, we do need to multiply by 3 there, for our 131 there. And if we do all that good stuff, let's see, 2 times 193 minus a 192 plus a 3 times a 131 going to give us negative 199 joules here, basically, as our delta S of the reaction. Any questions on that calculation? Again, this does not tell us whether or not the reaction is spontaneous, but it does tell us what's happening in the reaction. And is the amount of disorder increasing or decreasing? The amount of disorder is decreasing, right? The amount of order is increasing. We could predict that from our reaction, as we got 4 gas molecules there to 2 gas molecules, right? So we got 4 things flying around and end up with only 2 things flying around. So we increase the order. So our negative sign that we see here does make sense for the reaction as to what is going on. Now we can take care of our surroundings by doing our delta S of our surroundings is going to be minus delta H divided by our T. So we got to do a little conversion there, plus a 273 gives us 298 Kelvin on that. So I'm going to put this in here. It's going to be negative 92.6. I'm going to multiply it by 1,000. The reason I'm going to do that is to convert it to joules, because I know eventually I'm going to add it to this number. So might as well get them both in the same units. If you did not do that, then you would be in kilojoules at this point, and hopefully you recognize that at some point that you are there. And at this point here, we're going to end up with 92.6 times 1,000 divided by 298. And if you did convert it into joules, you'll end up with 311 joules. If you did not, then you would end up with obviously 0.311 kilojoules in that case, right? Any questions on that? This, yes, question? No? Okay. This also makes sense in terms of the surroundings, because what type of reaction is this? Endothermic or exothermic? This is a exothermic reaction where heat and energy is being released to the surroundings. It's a normalish temperature, which means the energy that's coming off from the reaction will make a good difference in the entropy of the surroundings, right? And we should expect the surroundings to increase the entropy, increase the disorder because of the energy that's coming from the reaction. And then we should end up with a delta S that is positive, which we did in this case, yes? So again, these are things that you can kind of check as you're doing your calculations to make sure that they sort of make sense, just in case maybe you mess up somewhere along the way. So to determine whether or not this reaction is spontaneous, we want to take the delta S of the universe will equal our delta S of our system, our reaction, plus our delta S of our surroundings. This is the part where having them in the same units is quite beneficial, I think. So that's going to be a minus 199 joules plus a 311 joules. You have this guy in kilojoules and you just added it, you have the wrong answer. Yes, so you got to watch those units definitely when you do it. So minus 199 plus a 311 looks like $1.12 there, joules as our delta S of our universe in this case. Yeah. Is this reaction spontaneous? This reaction is spontaneous because we have a delta S of the universe that is positive, yes? And that means that this reaction would occur heading in this direction towards the products. This is also a really good example of a reaction that is spontaneous, but can be really slow if you don't put a catalyst in it, yeah? So it will occur, but it might take a long time for it to occur. So again, a reminder that if a reaction is spontaneous, it does not necessarily mean that it occurs really fast. It just means that it should occur. Any questions on that? Yeah. The delta S of the universe, when you calculate that, if you have enough information to calculate that, if it is positive, then it is a spontaneous reaction, and vice versa. Obviously, if it's negative, it would be a non-spontaneous reaction. Other questions? All right, I think that's a good place to lay it up.